All right. I hope you guys are doing well, right? Hope you guys are enjoying this very special day, right? The very 1st of April. As the instructor, I figured that it's probably not a great idea to do pranks, right, in a lecture. But maybe it doesn't hurt to start a lecture in an unconventional way, right? Let's look at another game, just to start out. Remember last time we talked about this hypothetical context, right? We were looking at this binary versus decimal game, right? The class concluded that it's probably a good idea, right, to add the same numbers, right? We do x plus x, and with this x to be the power of 2, right? And turns out that, let me share the other screen. Let's see whether I can find it or not. Give me a sec. All right. Okay. So it turns out that some market, right, in Italy came up with the same idea a few years back. Right? We are already too late to conceive this game. I hope many of you have played with this game before. It's called 2048. It's basically a puzzle, right? This is a sliding tiles. The way you play this one is you want to grow this number, right, as large as possible. But look at what this game is doing, right? It's essentially the same with what we did, right? What we conceived in the previous lecture. Everything is a power of 2, right? And you try to grow it as much as you can. And with this kind of addition, it's really not right. It's not really expensive. We minimize the carry, right? And all we need to do is a single shift. Again, hopefully many of you have played with this game before. Right? It's actually a pretty fun game, and it's pretty addictive. If you haven't tried this before, I recommend it. Not now, maybe over summer. Right? Again, it's pretty addictive. And the reason I want to mention this game is because, let me come back to my main screen again. It's really because we are going to be seeing power 2 a lot in the 3 remaining lectures, starting from today. Okay. Here's my main screen again. In today's lecture, we're going to be talking about memories. Okay. And with memories, we have something called address space. And usually all the address space has a size of a power of 2. Okay. And similar to the CMOS lecture, well, actually we have a lot of things to discuss in this lecture. Similar to the CMOS lecture, this is where we're actually touching on a very rich topic. One lecture does not really deserve the depth of this topic. But my goal here is to give you guys a high-level overview of some of these key kind of memories, so that later on we can start using them to build our microprocessors. And also very similar to the CMOS lecture again. So this is where we are going to break this digital abstraction a little bit. We're going to play with some of this analog behavior to have in order to build very efficient and very compact memory. Okay. All right. I don't really have big announcements today. Just make sure that you guys are aware that homework 5 is due tomorrow. Okay. And also we're going to be posting homework 6 tonight. And we are going to be doing a quiz pretty soon. Right? This is the one that did not get a chance to finish last lecture. But to remind you guys what we did last time, we were introducing ALU, right? What is the full name of ALU, guys? Very good, right? Arithmetic logic unit. Okay, the reason that's called ALU is because we have an arithmetic unit like this, right, which can do add, right, sub. So these are the arithmetic operations. And we have a logic unit, a logical unit, which can do the logic operation like and, or, okay, and shift, right? SHL here means left shift. SHR here means right shift. In this case, we're using very simple. We're doing very simple shift where we just shift by 1 bit, either to the left or to the right. Okay. And given these operations, right, we need to come up with a binary encoding, right? Everything is binary in our system. So that's why we have something called OP, right, or opcode. Last time there's a good question about what are these, right? So these are basically hard-coded. Okay, so these are basically the encodings defined by the computer architect. Right? In our case, right, we use 00 to 3 zeros to indicate add, right, 001 to indicate sub, etc. Okay, and we are also in this ALU, right? We are now seeing some of the old friends, right? We've been playing with muxes a lot, right? This is 3 input mux. Last time we talked about this specific signal, right, which is driving the control, right, the selection of the mux inputs. We look at this O select, right, the output select. This is basically selecting from 3 different units, right? Basically the adder, right, logical unit, and shift. Okay, so the quiz is about this column, B select. Okay, just want to remind you again, we have this many different kind of operations, right? If you look at add, B select over here, right? This is B select. B select is selecting 00 because we want to do A plus B, right? We want to add the original B. And we also introduce the other, right? It's sort of like a meaningless operation, right? But later on, I'll try to make sense of it. Right? In some cases, we do need a meaningless operation like this. We call it no operation. In some cases, it's actually useful. Right? In this case, we are just passing A. Okay? And what we want to do is we assign A to Y, right? On the output side, what we really want to do is we want to make use of go through. We don't want to add additional wires, right? Why do we want to avoid additional wires, guys? Any ideas? Why don't we just add another wire, right? And assign to directly connect A to Y? What's the cost? What is the trade-off here? Delay, right? Glitch, right? And these are interesting points. So how do you add a wire? You cannot directly connect A to Y, right? Do you have to add something to that output mux? Yes or no? Yes, right? So to have, you want to do another, right? You want to do another Y pass A, Y equals A. You actually need another wire, and then you have to connect to this mux, right? Let me try to be clear, right? You need something like this. So that's going to add additional inputs, right, to the mux. Okay. Of course, in this case, it may not be clear whether this is indeed, right, harmful or not. But since we already have a connection from A to Y, why don't we just leverage it, right? Why don't we just assign B to be 0 so that Y equals A plus 0, which is A. Make sense? Right. So that's why we are doing this. Okay. Any questions about this ALU? Okay. Again, there are some other intermediate signals like LOP, SOPs. Right. So these are all generated by this so-called control unit or control logic based on the input opcode. And these are this is just a combination logic. Right? You guys can derive this using truth table and using kernel maps and such, right, to derive the actual circuit. But over here, it's just a black box. Okay, if there are no more questions, time. But let's look at another case. Same diagram, same ALU. We know how to do add, sub, right? Logical operations, shift operations, but how about comparison? Can we do equality check using this ALU? How do we do that? Any idea what is this one doing? Right, so if A, very good, right? If A minus B is 0, we have equality, right? Which means that this flag, right, is supposed to be 1. This is a 0 flag, Z means 0. Okay, so how do we do that? You look at this one, this is the NOR gate, right? But this is actually see here, this is a bus. This is an 8-bit bus. This is our notation, right? We have this slightly heavier line, a thicker line, then we have a slash, and then we have a bit width aside. This is an 8-bit bus, so really we have a NOR gate like this, right? This is NOR gate, which is Z, right, output side. And we have some inputs, right? We have 8 inputs, 8 incoming wires to this NOR gate. If one of these wire is a 1, one of this bit is a 1, what do we have? This is a NOR gate. This is an 8 input NOR gate, right? So if one of the bits, right? We have 8 bit. Y has 8 bits. If one of the bits is a 1, then Z is 0. Okay. Otherwise, if all bits are 0, we have a 1. Right. So that's how we detect equality. How about inequality? How do we check whether A, let's say, is no greater than let's do this. A is no less than B. What do we check? Is there a way to quickly check? MSB of Y, right? Okay. Alma, you have a question?
Yeah, my question is, what's the point of the 8-bit bus? Like, what does it do?
Point of the 8-bit bus. You mean the one that's connecting to the NOR gate?
Well, I guess just of all of them, like I didn't realize that's what they were. So why are they there?
Oh, okay, good question, right? So like I mentioned before, we are doing so-called fixed size operation, right? Later on, it's going to be more clear, maybe when I introduce memories, right? Later on in our microprocessor, we are not going to be adding just a 1-bit value. So pretty much all the values are going to be stored in the so-called fixed size words. In the current microprocessor, they are usually 32-bit or 64 bits. So those are the word size. Okay. And in the 2300 word, right? Let's first build a simpler ALU, simpler microprocessor. Let's say the word size is just 8. So basically all the values, okay, are represented by 8-bit integers. Okay, so that's the assumption. Make sense?
Yeah, just one follow-up question. Like for instance, on the wire for A, how there's 2 8-bit buses right after each other. Isn't that not possible?
That's just one.
Oh, it's just
one.
This
one. That's one. Just one. I just want to make it clear that we have 8 bits, right? So right before the adder.
Oh, so okay, thanks.
Okay. So this is the same wire. Good question. Okay, and right, so we just talk about this, right? We can actually use the ALU to check comparison as well, right? To do comparison, check equality and inequality as well, by just looking at Z flag and MSB. All right, any questions about ALU? Again, you guys will be building ALU, right, in the final lab, right? Okay, so now let's switch gear. Let's talk about memory. We are actually almost there. We're going to be talking about the microprocessor, right? I've been showing this diagram to you more than once, right? We just look at ALU. Now let's look at this so-called data memory or data RAM. RAM is random access memory. I'm going to define it pretty soon. Okay. Once we have understanding of this key, right, some of these basic building blocks, we'll be looking at how to actually build a real thing. We actually need a lot of memory, right? You guys probably know when you buy a computer, right? So I think I asked you guys before, right? One thing you want to check is how many cores you have, right? What is the operating frequency, right? Is it a 2 gigahertz microprocessor or 1 gigahertz, right? That's one of the important specs. The other one is you probably want to check, right? How much is the main memory? This is where we usually have so-called DRAM. Okay, I'm going to explain that. But why do we need a lot of memory, right? We have been just dealing with 1 bit, right? 2-bit or 8-bit value, or maybe up to 32 bits. To give you guys some intuition. So let's say, I guess most of you have, come across this notion called HD, right? HD TV, high definition TV, right? HD screen. These, of course, we are talking about 4K, 8K, which are even higher resolution. Anyone knows what is HD in terms of the dimension? Just the regular 1080p. 1080p HD. What is the dimension? Anyone knows? Very good. Great. Okay, this one, right? 1920. This is the size, right? The resolution. Okay, we have this many pixels basically on the screen, and each pixel has this sort of RGB, right? red, green, blue. So these are 3 key color components. Each one requires 8 bits. Okay, basically 3 bytes or 24 bits. Let's say 24 bit. Okay, so roughly how much is this? This is just one frame, right? This is just one frame. One frame, one HD frame. We already need this many pixels. We already need this many bits. Any rough idea? So this one, if you look at this part, this is roughly, maybe 2 million, something like this, right? Roughly. Okay, so basically, the EV, right? So also include the RGB part, we have roughly this much, right? Makes sense, right? This is one frame. And do you guys know what is the typical frame rate for us to have a pleasant, right, viewing experience? Right, that's 60 frame per second. Right. Okay, what does this mean? It means for just 1 second worth of content, right, the video content, we need this much, about 60 frames, right? So roughly, this is how much? This is 3 GB, right? Roughly 3 gigabits. This is a lot, right? Just 1 second. This is where, of course, right? I haven't mentioned the compression, a lot of video codec, right? Compression comes into play, right? To really sort of squeeze this. But hopefully this gives you a sense, right? Indeed, we need a lot of memory. We need to store this somewhere, right? And we actually need to store it in a cost-effective way. In case you guys are not familiar with, M and G, so just want to quickly ask, right? What is the mega M? It's also power of 2, in terms of power of 2. I started out the lecture, right? It's power of 2. Power of 2, not power of 10, guys. Very good, right? 10 to the 6, right? Anyone else, right? If you say mega in terms of power of 2, what is that? It's actually, first, when we say K, right? KB or K byte, usually we say, this is 2 to the 10, right? About 1,000. Okay, mega 2 to the 20. Okay, G, what's G? Giga 2 to the what? 30. Very good. Okay, keep these numbers in mind. Right? These are good to know. Okay? And when you click the file, right, you see the file size, right, megabytes, right, gigabytes. Right? This is the order, 2 to the 20 to the 30. Okay, and usually, when you buy a memory, you have like 8 gigabytes, right, 16 gigabytes, right? This is again, you can quickly translate how many actual bits you have. All right, so hopefully you guys are convinced, right? We do need a lot of memory. But what exactly is a memory? First, let's just talk about this abstract. Let's just introduce the memory in a more abstract way. It's basically a 2D array, right? For example, in this case, I have a very small memory. It's a 4 by, I think right over here. It's a 4 by, somehow one of the rows, one of the lines not showing up here on the screen. So it's really a 4 by 3. We have this many bits. And with this memory, usually we have data, right? We have data inputs and outputs, right? Depending on whether this memory is read-only or it's both readable and writable. Okay, we have data inputs and outputs. And the other thing is these memories are usually addressable. And this is a really important concept for memory. We have something called address, right? And usually for these 2D arrays, it's usually organized, okay, in terms of, right, again, the X dimension and Y dimension. So usually we call this one, right, X. This is the width of the memory. And this is the depth of the memory. Okay. And for the width, right, we usually call it a word. This is where the notion of word comes into play again. For my very small memory, this is actually not a very typical memory. This is just a toy example. We have a 3-bit word here. Okay, and what the address does is, so when you are given address, So if the address is 11 in this case, right, we are going to select the top word. If the address is 00, we're going to select the bottom word. With the data, on the data output side, if address is 00, we're going to see 011, okay, the bottom word. If the address is 11, we're going to see 010, the top word. And we're going to grab all the bits from this word all together. Okay. It's not bit addressable, it's word addressable. So for my abstract memory, does it make sense? Okay. Again, given 2-bit address, right, we can address 4 words, which is shown here. And again, coming back to the modern microprocessors and also modern memories, usually the word size is 32 or 64. Okay, but the memory later on I'm going to see those are byte addressable. And also when you guys are playing with your software program, right, in case you have some software programming experience, when you use int in Java or C, those are usually 32-bit, okay, 32-bit word. And we even use character or char in C, that's an 8-bit word. All right. Okay. So let's see. Somehow my screen. Okay, good. Okay, so this is actually, I just showed you the abstract view. This is a more realistic physical view. This is how the memory usually organized. We have an array, a 2D array of bit cells. And this bit cells, each one of this is a bit cell. Okay. And this bit cell store the bit. Right? It's a bit cell, and the bit cell are arranged in the word. Right? Each horizontal line is the word. And each bit cell is connected to a word line over here and a bit line. The bit line actually grab the data, either input or output the data, actual bit. Okay, and this is again a more realistic physical view of the memory. And when we enter address, okay, when we put in address here, usually, right, only one word line is hot, is asserted at any given time. Okay. So if you want to do this, what is this box? This is also a combinational building block that we have been playing with for a while. You know, we just got to see mux, right? Very good, right, Devin? Okay. This is a decoder, right? This is the 2 to 4, to be more precise, right? 2 to 4 decoder. Think about decoder, right? Only one of the lines, output lines, is hot. Okay. And this is where, you know, decoder becomes really useful. It's actually used in the memory a lot because we want to decode the address. We're going to decode the binary address into this called one hot format, right? So that every time, so one of the word lines is hot, is asserted. Any questions so far about this memory? Again, things are very abstract right now, right? Okay, but the key thing is, the key concept is that we have these bit cells to store the 0 1s, and we have these word lines, right? The bit cells are connecting to word lines and bit lines at each, right? At any given time when we enter address, so one entire word line, okay, will be hot, and then we'll grab data from the entire word. Okay, that's how the memory is addressed. We can either read it or write it. We're going to discuss it, okay, in using separate cases. All right. Okay, so here are the major types of memories. We have something called ROM. We're going to start with that. It's a read-only memory. So this is where we really don't care about the writing part. With a ROM, usually the contents are fixed at the design time or at the factory time, and it's not going to be written again. Right? So this is where we have a truly read-only memory. But these days, there are also ROMs which are rarely written, but mostly read. Okay? And that's where the write access is much slower than the read access. So in some cases, people also call it a ROM. And usually it's a non-volatile for ROM, meaning that once the contents are put in right into the memory, it's going to be there regardless of whether there's power or not. Okay. That's where we have sort of a non-volatile memory. Okay. And we're going to start with ROM for this lecture. And later on, we're going to look at RAM. RAM means random access memory, which is writable. Okay. We're going to look at this later. Let's start with ROM. Again, it's the content, right? Its content is fixed at the factory time, or rarely written. So same diagram, pretty much the same, but see here, so the right, these data lines, these are unidirectional. Right? We only have outputs here. Okay. Then we just talk about memory a lot, right? So let's say if I give you a, just want to make sure that you guys understand the notion of this address. We just talk about, right, the address, right, the giga, right? So GB, right? So let's say we have a 4G small b, 4 gigabits memory. Okay. How many address lines do we need? Can you guys translate? Right, see here, given n address lines, right, we can address 2 to the n. What's on ROM? Okay, it does not matter at this point, but let me try to make it simpler. Okay, by 4G words, very good. Okay? Words, we don't care how many bits do we have in the word. Log, right, very good. Log 4GB, which is what? Is it 30? G is 2 to 30, right? That's something that we just agreed. And 4 is 2 to 2, right? So basically we need 32. That's okay. All right. Okay. Hopefully you guys can be familiar with this, comfortable with this pretty soon, right? 2 to 32 is 4 GB. Okay. If word is 8 bytes. Okay, coming back to the ROM, right? We have this array, right? We have 2 to the n number of words, and m is the word size, right? This is the word size. And we have a decoder. All right, so let's quickly look at how we can cheaply fabricate a ROM using MOS transistors, MOS transistors in this case. Okay. This is actually one way to do it. So we really fix everything at the factory time, and it's not going to be written again. Okay, let's try to decipher this thing. This seems sort of convoluted, right? It's actually not that bad. This is also a good way for you guys to refresh your mind about NMOS. NMOS is active low or active high, guys? NMOS. When does it conduct, right? When we have a 1, right, on the gate. So when we turn on, let's say we have an address, right? So we turn on this word line, the very top word line. Okay. What's gonna happen to this line, to this output? This one. What's gonna happen to this one? What is the value? Forget about the inverter right now, okay, for now. Okay. What's gonna happen? What's the value of this line, this signal? If you try to read this diagram. Now, there are some resistors on the top, right? It's gonna be low, right? On your right. Why is it low? Because with the word line asserted, this specific NMOS, right? This guy is conducting, right? This guy is on. If this NMOS is on, that means this line again is connected to what? To ground. Do you guys see the connection? Okay, right? And so in the end, on the opposite side, since these are inverted, we have a 1, right? So this is equal to 0 if the word line is high, right? And in the end, on the output side, we have a 1. Okay, so what does this mean? It means that, so we just need to look at the conjunction, right? So each bit cell is at the junction, right? The junction point, right? Each bit cell is at the junction of the word line and the bit line, right? That basically defines the position or the index of this bit cell. So what does this NMOS mean? Does it encode a 0 or 1? You put the NMOS there at that junction point. 0, 1, guys. for this ROM to work. Any questions so far about what's going on here? Feel free to ask, right? Okay, again, what I'm asking is, what is this NMOS exactly doing? With ROM, right, it's a read-only memory. We want to hard code either 0 or 1, right, in each bit cell. So this junction point basically is a bit cell, right? My question is, if we have a NMOS there, what does that represent? Is it a 0 or 1? It is a 1, right? Okay, you're right. We just talk about this, right? It is the 1. Because when the NMOS is conducting, it's gonna drive the line here, right? This line, it's gonna drive this line to low. And this line is gonna be inverted. So of course, this NMOS encodes or hard codes a 1. Okay, if there's no NMOS, then we have a 0, right? For that corresponding bit cell. Okay. All right, so I'm asking, so do the lines coming out of the decoder just pass the address? Just pass the address. Okay. Let's say, forget about this thing, right? Let's say we don't have ... here. Okay, so let's say we have, 4 words. Okay, 4 words. Okay. Do you want to explain this again? Right, then how many bits do we need? Come on. 2 bits, right? 2-bit address, right? Okay, so then we have a 2 to 4 decoder, right? I just want to repeat this again. So if the address is 1, 1, okay, we associate each word line with index, right? Sorry, this is 0, 0. Okay, if the address is 1, 1, what does that mean? It means that we want to select word 3. Okay, we want to read word 3. 3 is 1, 1. The address is basically an index, right? This whole thing is basically like a lookup table, right? Like we enter the address, right? And then we're gonna find a corresponding word that has the same address, that has the same index. Is it clear? Okay, essentially, with this decoder, right, it's basically decoding the address in the binary format into this 0, 1s for each word line. And exactly only 1 word line is hot, is asserted, which is the word that's selected. Any other questions? Okay, about this one? So basically these things, right? Okay, the each NMOS over here encodes a 1. Okay. Because we invert, right, everything in the end. The reason we are inverting this is because if there's no NMOS, right, see here, we do have some resistors, right? The resistor will drive the voltage low, right? If there's no NMOS, then we're gonna have a poor 1, right? It's a low 1 with low voltage. That's why we need an inverter. It's sort of like to further strengthen the signal. But this is sort of a lower level deal. We don't understand this, don't follow this, this is fine. All you guys need to understand is over here, right? When we put an NMOS there, we can actually cheaply fabricate, right, a 1 for this ROM. Okay. This is the one way to implement ROM. And actually, there are many applications of ROM. We actually see them in for storage, for storing both data and program. In the past, right, when you open up your phone, the logo that shows up, right, at the beginning, so that pattern, that image pattern is most likely stored in the ROM, because that one doesn't change. Of course, now everything is configurable and programmable. Okay, and also there are many embedded systems like like a wash machine. There are some digital systems. They're digital computers, very small, very tiny ones. Those are so-called embedded systems. There, the program is usually hard-coded. It will never change, right? Once the machine is deployed, you don't need to reprogram the machine anymore. that's where we can just use a ROM to store the program. Okay. And there are some other interesting use of ROM as well. Actually, we can use them to implement conditional logic. All we need to do is to use the address bits as the function inputs, and the data outputs will become the function outputs. Right? Hopefully, this is intuitive enough, right? All we are doing is basically we put the truth table to the ROM, and we hard code the function. So see here, the nice thing is with the ROM, we can actually implement a multi-output function. Right? See here, we have there's a 4 output function. Right? We have some minterms here. Right? We can quickly derive the truth table. And all we need to do is, if we have a ROM, right? If you actually want to hard code this function using the ROM, we just have to put the truth table, just hard code the truth table in this memory array. Right? That's it. And we connect the input, right, ABC, to the decoder side as the address bits. And this just works. Make sense, right? Because we actually also talk about using decoder to implement conditional logic functions. This is basically the same idea. Right? From the decoder side, you have this minterms, right? From the output side. Any questions so far? Yes. Okay. Right. So in this case, we are using A words, right? A words, each word basically encodes 1 row in the truth table. This is correspond to a word. All right. Okay. Hopefully this is very intuitive. Right. Okay. And output side is just the data, right? So we can just connect F0 all the way to F3 with the data outputs of the ROM. Okay, right. So if this is clear enough, let's do something more interesting. Okay, so going forward later on, I'm gonna add some so-called bonus question in each lecture. Okay, where you guys have to do a quick context. Right? I'm gonna ask you guys a question, a non-trivial question, and I'll give the whole class, 10 seconds to quickly think about this. And when I signal, right? So, but you need to wait for my signal. Don't enter a question. Don't enter answer in the chat window. Okay. When I give you the signal, you guys raise hand. Okay? And I'm going to call out names. But if you have an answer, the first who give me the correct answer will get the bonus. And I'm not going to define the bonus today. Since this is actually not a good day to make promise. Okay? I'm going to tell you what exactly is the bonus in the next lecture. But this one is just a warm-up, right? So this is not a real context, right? For today, let's just do a quick warm-up to see how exactly does this bonus question work, bonus round work. Okay, so I'm gonna give you a ROM. This is a 14x4 ROM. Okay, this is a ROM. Okay, 14x4. What does this mean? It means that we have, sorry, not 14, 16x4. We have 16 words. Okay, and each word is 4-bit wide. Is it clear? And these are the inputs, right? They are connecting the addresses, and these are the data outputs. Okay, and here's the content of the ROM, right? Okay, these are addresses, right? And the corresponding outputs. Of course, these are hard-coded in the ROM. My question for the classes, again, this is a practice bonus round, right? So what exactly is this ROM implementing? What is the function of this ROM? I'll give the whole class about 10 seconds. So all of you get to read the question, and I'm going to give you a signal, right? So once you have the answer in mind, raise your hand. Don't put it in the chat window. I do want the whole class to look at it. Let's think about it. Is it clear? Is the question clear? Okay, so this is basic content of ROM. All right, so I'll give you guys about 10 seconds, and then I'll let you know. when to raise hand. All right, guys, go for it. Emma.
Z equals X times Y.
Very good. Excellent. Okay, can you explain? Can you quickly explain, just in case? Because I think a few other people also raise hands. Right. I have to go with the order.
Oh, you want me to answer
Yes,
this?
yes. Why is it a multiplication?
Well, all the ones that have x1, x0 equals 0, 0, or y1, y0 equals 0, 0, have the whole answer be 0. So I figured it was something to do with multiplication. Then you see it goes 1, 2, 3, and then 2, 4, 6, and 3, 6, 9.
Excellent, right? So for those ones, it seems pretty obvious, right? You know, if one of the operands, actually y and x, there are two operands, input operands, right? If one of the operands is a 0, then we have a 0. Okay? If you are still not convinced, this is actually a multiplication. Look at this, right? This one, this is what? This is a 9, right? Okay, and we have x is 3 and y is 3. Okay, 3 times 3. Okay, great job. Is it clear, guys? Okay. All right, so we are going to be doing this hopefully in most of the lectures going forward. I'll pick out some non-trivial question and ask the class. Okay. And also, last time we talked about how to implement addition, right? How to implement subtraction. We've never talked about how to implement multiplication. This is actually one way. But is this a good idea in general for implementing a multiplication, guys? Is this a good idea? Why not? What's wrong? Many of you know. Very good, right? Gavin, you're right, right? This works for multiplying numbers with small bits. If you haven't have the ROM or memory, you can just hard code the input and output correspondence, and that's straightforward enough. But in case you have, this doesn't really work, right? For 32-bit inputs, you're gonna have to use a very large memory. That's just exponential, right? It may not be a good idea. Okay, all right, so in general, if you actually want to use ROM, this indeed used, right? It's actually used in many cases to implement very simple functions. If you do have a ROM handy, and we don't really want to go through the the exercise of doing all sorts of optimizations, and all we have just a ROM, then we just need to put in the truth table. That's it. Okay, the design time is very short, but in general, this is not a good idea for functions with large input size. Right? First, this is exponential, right? This is a truth table. We already talked about this. This is exponential, and we really cannot exploit, some of the properties of the function. For example, don't cares. You cannot really optimize it, right? So for arbitrary functions, this is not a good idea, but it is useful in some cases, some special cases. All right, great. This is ROM. Any questions about ROM?